Hello students, welcome to the channel Physiology Redefined. In my earlier video, I discussed about the detailed structures of the heme part of the hemoglobin molecule. And now is about the detailed structures of the globin part of the hemoglobin molecule. So please keep on watching till the end to get the clear idea, clear concept regarding the structures of the globin and thereby the entire hemoglobin. If at the end of this video, if you like this class, if you like the concept, if the concept becomes clearer to you, please press the like button, share it to your friends and subscribe this channel if not yet subscribed. So let us now talk about the structures of the globin in details. As I told earlier also, that hemoglobin is comprised of heme part and the globin part. Now globin is basically comprised of four polypeptide chains. So as per the primary structures of the globin is comprised of four polypeptide chains, and two types of polypeptide chains are there. Out of these four polypeptide chains, two are known as alpha chains. Two alpha chains are there, and two non-alpha chains are there. It can be the beta chain, it can be the gamma chain, it can be the delta chains, depending on the varieties of the hemoglobin in the human beings at the time of the birth. So let us now see about the difference of the different chains of the globin molecules under the primary structure. So first is type of hemoglobin varieties. Second is the percentage at the time of the birth, percentage content. Second one is the composition of the chain, polypeptide chain, and lastly the difference of amino acid in the chain. So first is regarding the first variety, which is known as the hemoglobin major, which is otherwise known as HbA1. This is the maximum percent of this variety is maximum, which is around 97%, and this is comprised of two alpha chain and two beta chain. So two alpha chain and two non-alpha chain, that includes beta chains. So 97% of the hemoglobin, major hemoglobin in human beings at the time of birth, that is 97%, is the alpha 2 beta 2. Composition of the alpha chain, this contains 141 amino acids, and beta chain is comprised of 146 amino acids. Now regarding the second variety, this is the number one variety. Second variety is known as hemoglobin minor. This is also known as the hemoglobin A2. This percentage of this one is around 2 to 3%. So this is why it is minor hemoglobin. This is minor hemoglobin, and this is comprised of two alpha chain and two delta chain. Compositions of the alpha chain is 141 amino acids, similar to that of the alpha chain here, and composition of the delta chain is also 146 amino acids, but last 10 amino acid differs. The difference of last 10 amino acids from that of the beta chain in case of delta chains. Now is about the third varieties of the hemoglobin, which is known as the fetal hemoglobin. Fetal hemoglobin, this is also known as HbF. At the time of the birth, only negligible amount of the fetal hemoglobin is present, which is around 1%, and this is comprised of 2 alpha chain and 2 gamma chain. 2 alpha chain and 2 gamma chain. Here again, alpha chain comprised of 141 amino acids and gamma chain comprised of 146 amino acids, but the last 37 amino acids, the difference of last 37 amino acids. So this is about the compositions of the or varieties of the hemoglobin present in case of human beings at the time of the birth. Before birth, at the embryonic life, in case of human beings, in the embryonic life, there is another type of hemoglobin is present, which is known as the embryonic hemoglobin. Embryonic hemoglobin. And this embryonic hemoglobin composition, this is generally present before 8 weeks of gestation. Before 8 weeks of pregnancy or before 8 weeks of gestation, this type of embryonic hemoglobin is present in case of human beings, which is comprised of epsilon 2 and zeta 2 amino acid chain or polypeptide chain, epsilon 2 and zeta 2 polypeptide chain. So this is about the primary structures of the hemoglobin. So globin is comprised of 2 alpha chain and 2 non-alpha chain. It can be beta, it can be delta, it can be gamma. So now is about the secondary structures of the hemoglobin. Secondary structures of hemoglobin. So, as per the secondary structure of hemoglobin, each of the polypeptide chain of the hemoglobin, alpha or beta, delta or gamma, whatever it can be, these are alpha helicals. So, as per the secondary structures of the globin molecule, it is alpha helix. It is comprised of alpha helix or alpha helical. Each and every polypeptide chain is alpha helical or alpha helix. And in this case, what's happening? Each of this alpha chain or beta chain, that is alpha helical, this is comprised of each of these beta chain has 8 segments, 8 subsegments. Alpha helix of beta chain has got 8 subsegments A to H, whereas the alpha helix of the alpha chain has got 7 segments, 7 subsegments. This is also A to H, but here except the D chain, except the D subhelix or subsegment, except D subsegment or subhelix, D subsegments. So each of the alpha chain or the beta chain, they are comprised of they are alpha helix in structure, and beta chain has got 8 subsegments, alpha chain has got 7 subsegments. And here you can see, suppose this is the alpha helix, here is the NH2 terminal amino terminal group, this is the A subsegment, B subsegment, C subsegment. After C subsegment, there is a loop, and this loop connects with the E subsegment. In case of alpha chain, then again there is a loop, which is connected with this is the E, this is the subsegment F, then again there is a loop, which is connected with the G segment, and this is again connected with the H segment. Then there is the carboxy terminal group, and this H segment and the G segment, this is the G1, this is the G segment, this G1 is connected with the again another loop, that is known as the HG loop. So there are different segments. This is in case of alpha chain. This is about the alpha helical structures of the alpha chain. So it is comprised of A segment, A subsegment, B subsegment, C subsegment. D is absent here, as I told, D is absent here. E subsegment, C and E, this is joined by a loop that is known as the CE loop. Then again E and F is joined by a loop that is known as the EF loop. Then again F subsegment is joined with the G, and this is known as the FG loop. And then again G and H is joined with a short segment that is known as the HG. So this is the alpha helical structures of the alpha chain, and here at this part there is another thing I want to mention, that each of the globin chain has got 36 histidine residues. Each of the globin chain has got 36 histidine residues, and these histidine residues are required for the buffering actions of the hemoglobin. Now, out of these 36 histidine residues, in case of alpha chain, the 58th residue of the F chain, this is known as the proximal histidine or F8. In case of beta chain, it is 63rd histidine residue. 63rd histidine residue is known as the F8 or proximal histidine. So this is known as the proximal histidine or F8. Whereas in case of alpha chain, 87th histidine residue of the E chain that is known as the E7. This is the part, this is the which is known as the E7, and this one is known as the distal histidine. Distal histidine. This is in case of alpha chain. In case of beta chain, the 92nd residue is known as the distal histidine. So F8 and the E7, these are very, very important things. These residues are very important things because at these F8 residues, the ferrous ion is covalently linked. So ferrous ion this is linked with this F8. This is linked with the F8. So this is about that is the proximal histidine is linked with the ferrous ion. So in this way, heme molecule, ferrous ion of the heme molecule gets attached with the F8 or proximal histidine of the alpha chain or the beta chain, and thereby globin molecule, each of the globin molecule is linked with one protoporphyrin ring, the iron atom of the protoporphyrin ring, that is the heme molecules. So this is about the secondary structures of the hemoglobin. Now is about the tertiary structure. Tertiary structure of the hemoglobin. So as per the tertiary structure means each of the globin chain is tightly packed. Each of the alpha helix of the globin chain, alpha chain or the beta chain, they are assembled in such a way so that they look like a tightly packed protein molecules. They look like a tightly packed protein molecules. That means this is suppose one polypeptide chain, another polypeptide chain, another polypeptide chain, third polypeptide chain, and the fourth polypeptide chain. So all of these chains, 4 chains, are tightly packed with each other by the help of the hydrogen bonds, by the help of the covalent bonds, and by the help of the salt bridges, that is the attraction of oppositely charged amino acids of different chains. So by means of 3 bond structures, these 4, this is suppose alpha, this is suppose beta, another beta, this is suppose another alpha, alpha 1, this is alpha 2, this is the beta 1, and this is suppose beta 2. In this way, 4 polypeptide chains are tightly packed with each other, and they are bound with each other by the help of the hydrogen bond, covalent bond, and the salt bridges. Now, in each of these hemoglobin molecules, in each of the polypeptide chain, as I told, the iron molecules are attached. In each of these molecules, the iron molecules are attached. So here is the one iron molecule. Here is suppose another iron molecule. Here is suppose another iron molecules. Here is suppose another iron molecule. So in each of the chain, 1 iron molecules are attached with the globin chain. Now what's happened? How this ferrous ion gets attached with the alpha helix or tightly packed globin chain? Here you see. Suppose this is the one pyrrole ring, another pyrrole ring, third pyrrole ring, fourth pyrrole ring. These are the four pyrrole ring. And as I told, at the center of the pyrrole ring, tetrapyrrole ring, and these four pyrrole rings are bound with the methylene bridge. They are bound with the methylene bridge. They bound with the methylene bridge. And I told that at the center of the tetrapyrrole ring, there is a ferrous ion. There is a ferrous ion at the center of the tetrapyrrole ring. Now what's happened? This F8 position of the globin chain, alpha chain or the beta chain, at the F8 position of the alpha chain or the globin chain, whatever histidine residues are there, they are linked with the, so F8 alpha chain or the F8 residue of the proximal histidine residue of the alpha chain or the beta chain of the globin molecule, they are covalently linked with the ferrous ion. And the F7, E7, these are not linked with the ferrous ion, but these are lying in a plane, in a single plane, in a plane of the heme ring. That is, in the heme ring, the E7 and the F8 ring, this plane, the ferrous ion is there, and the ferrous ion or the heme molecule is perpendicular. This ferrous ion is the heme molecule is perpendicular to this axis, this plane. At this E7, F8 plane, the heme molecule present in the particular form, in the perpendicular form, in the perpendicular way, the heme molecules are present in between the E7 and F8 straight line. Though the ferrous ion is covalently linked with the ferrous proximal histidine residue, that is the F8 residue. However, this ferrous ion is not exactly on the plane of the heme ring. It is not exactly plane of the heme ring. Suppose this is the heme ring. This is one heme ring. This is the another heme ring. At this heme ring, as I told, the ferrous ion is perpendicular but not in a same plane. So this is the ferrous ion. Here is the nitrogen molecules of the tetrapyrrole ring or the pyrrole ring. So this ferrous ion is not at the exactly at the plane of the heme ring. They are not exactly at the F8 E7 heme plane. This distance they lies about 0.06 nanometer above this plane. They lies 0.06 nanometer above the plane once the hemoglobin is in the deoxygenated condition, deoxygenated state. So once the hemoglobin is present in the deoxygenated plane, deoxygenated state, the ferrous ion lies 0.06 nanometer above the heme ring or the plane of the heme ring. So this is all about the tertiary structures of the hemoglobin. So now is about the quaternary structures of the hemoglobin. Quaternary structure of the hemoglobin. So now is about the quaternary structures. So that is the final form of the globin structures. So as I told that 2 alpha and the 2 beta chains are present in the hemoglobin, in which the alpha beta forms are there. So here is suppose the alpha chains, 2 alpha chains are there. The hemoglobin molecule is comprised of 2 alpha chains and the 2 beta chains. But in such a way so that these are not these are not homodimer. That means alpha 1 is not bind with the alpha 2, or the other alpha 1 binds with the beta 1. Alpha 1 binds with the beta 1 or beta 2, whereas beta 1 binds with the alpha, beta 1 binds with the alpha 1 and the alpha 2. So these are not homodimer, rather the heterodimer. So globin molecules are heterodimer. As per the quaternary structure, they are the heterodimer structure. That means what's happened? Suppose this is alpha 1 binds with the beta 1 and the beta 2, whereas the alpha 2 binds with the beta 1 and the beta 2. In such a way, here at 4 contact points. So alpha, these four molecules, 4 polypeptide chains, they lie in such a way, these heterodimers are lying in such a way so that there are 4 contact points. So this is the contact point 1, suppose contact point 1, contact point 2, contact point 3 and contact point 4. Out of this contact point, what's happened? The A1 position and the 3 positions, 1 and 3 positions, they do not change once the configurational change of the heterodimer are initiating during the oxygenation process. This configuration is not changed. This heterodimer do not change its position. They rotate in relation to the other dimer. That means because the contact between the alpha 1 and the beta 1, that is 1 contact point 1 and the 3, there is strong contact point and no rotation, strong contact, and thereby no rotation is possible. Whereas rotation possible at 2 contact point 2 and the 4, there is a loose contact, and here is the rotation is possible. During the oxygenation process, rotation possible at the alpha 1 beta 2. So here you see, suppose this is the alpha 1 dimer, alpha 1 and the beta 1 heterodimer, alpha 1 and the beta 1 heterodimer, and this is about the alpha 2 and the beta 2 heterodimer. This is the configurational change, quaternary structures of the hemoglobin molecule in the deoxygenated state. Once the oxygenation starts, then what's happened? There is a 15-degree rotation from the axis. This is the axis of the 2 heterodimer. 2 heterodimer axis is this. From this axis, here you see the 15-degree rotation is there. 15-degree rotation is initiated from the axis. So there is a enter alpha 1 and the beta 1 dimer. They rotates in relation to alpha 2 beta 2. Entire alpha 1 beta 1 dimer rotates in relation to alpha 2 beta 2. So this is the shifting of the plane or the axis now. So in this conditions, what's happening? The configuration of the alpha 1 and the beta 1, they remain same and they rotates from the axis, and thereby their relative change, their movement in relation to the alpha 2 beta 2 gets changed. In relation to the alpha 2 beta 2 dimer, their movement gets changed. Whereas the specific heterodimer, that is alpha 1 beta 1 and the alpha 2 beta 2, they remain unchanged. This dimer position is changed in respect to the alpha 2 beta 2 dimer. So this is about the quaternary structures of the hemoglobin molecule. So now this quaternary structure gets changed during the oxygenation process. That means once the oxygen binds with one hemoglobin molecule, then this quaternary structure gets changed. Some configurational change of the quaternary structure of the hemoglobin takes place. So let us see how this changes takes place once it binds with the oxygen molecule. So once the hemoglobin is in deoxygenated state, then what's happened? All the four globin molecules of a hemoglobin molecule are tightly packed. That means alpha 1, alpha 2, beta 1 and beta 2 all are tightly packed, and this tightly packed hemoglobin molecule is known as the tense hemoglobin. So suppose in the deoxygenated state, the hemoglobins are in tense state. All the four molecules of the hemoglobin, first one, second one, third one and fourth one, all remain in the tense state. That means in this tense state, T state, the affinity of the hemoglobin towards the oxygen is little bit less. Now what's happened? Once the oxygen gets bind with this one molecule of the T1, this one, so if oxygen binds with this T1 molecule here at the first molecule, this is the first molecule, suppose. So once the oxygen binds with this first molecule of the hemoglobin molecule, first component of the hemoglobin molecule or first subunit of the hemoglobin molecule, then what's happened? They are transformed into the R state or the relaxed state. So they will now transform into the R state or the relaxed state. So suppose this is the relaxed state. This will be now relaxed state. So remaining units will be T state, but the hemoglobin subunit in which the oxygen gets bind, that will be transformed into the R state or the relaxed state. And this switching from the T state to the R state is known as the TR switch. TR switch. This is known as the TR switch. So TR switch takes place during this phenomena. Now what's happening? Let us see how this TR switch takes place, or why or how this tense state gets transformed into the R state. So here you see, as I told, this is the once the deoxygenated state, this is in deoxygenated state. The hemoglobin molecules are configurations, quaternary structures are like this. In this alpha 1 binds with the beta 1, alpha 2 binds with the beta 2. Now once the oxygen combines with the 1 molecules, that is suppose alpha 1 molecules, 1 globin chain, the ferrous ion of the 1 globin chain, suppose alpha 1. Then what's happening? There is a movement of the 15-degree movement of the alpha 1 beta 1 dimer. So here you see alpha 1 beta 1, this is the alpha 1 beta 1 dimer. This is rotation of 15-degree rotation from the axis takes place of the alpha 1 beta 1 dimer. That means alpha 1 beta 1 dimer is moved 15 degree from the axis. They move, this is the main axis. From the main axis it is moved, this is the change axis. So from the main axis there is a 15-degree rotation of the alpha 1 beta 1 dimer in respect to alpha 2 beta 2 dimer. That means alpha 1 beta 1 movement is changed in respect to alpha 2 beta 2. And this here you see, this is the position, change position of the alpha 1 beta 1 now. This is the change position of the alpha 1 beta 1 now due to the combinations of the binding of the oxygen with the 1 globin chain. Now what's happened? As now this movement is taking place, alpha 1 dimer, alpha 1 beta 1 dimer moves in relation to alpha 2 beta 2. What will happen? Resultant effect will be pulling of the iron atom of the hemoglobin of the heme molecule towards the plane of the heme ring. If you can remember, that's in the deoxygenated state, this is suppose the heme ring, this is the heme ring in the deoxygenated state, and as I told earlier also that this is the protoporphyrin ring on which the ferrous ion is attached. Now this ferrous ion, as I told, is beyond 0.06 millimeter above the heme ring, plane of the heme ring. So they do not lie at the same plane of the heme ring. This is in case of deoxygenated condition. So once the oxygen gets bind with this, then what's happened? Because of this movement, because of this tear switch, what's happened? This will be now come in the plane of the heme ring. So this is the heme ring, this is suppose the heme ring, this is the pyrrole, and this will be now this ferrous ion will come in at the plane of the heme ring. So this ferrous ion will come at the plane of the heme ring because of the movement of the alpha 1 beta 1 dimer from the axis in relation to the alpha 2 beta 2 dimer. So these changes will take place. So now once these changes will take place, ferrous ion will come at the plane of the heme ring. Then what will happen? As I told, this is the pyrrole 1, pyrrole 2, pyrrole 3, pyrrole 4, and here is the ferrous ion. So 4 valency of the ferrous ion is attached with the 4 pyrrole rings, and as I told, 5th valency of the ferrous ion is attached with the proximal histidine residue of the alpha chain or the beta chain. So this one is attached with the alpha chain or the beta chain, a proximal histidine residue. Now what's happened? Because once the ferrous ion will come at the same plane of the heme ring, then what will happen? This ferrous ion will pull the F8 towards it. This ferrous ion will pull this F8 towards this position. So F8 will be now pulled towards the ferrous ion. So pulling of the F8 proximal histidine towards the ferrous ion. And because of this pulling, what's happened? The salt bridges by which the other globin molecules are attached with this molecule. So here you say this is another molecule, second, third, and fourth. So once these changes is taking place, once this T molecule is converted to the R state, relaxed state, then what's happened? The salt bridges, because of the pulling of the F8 towards the Fe2, the salt bridges by which this T molecule, this T molecule, this T molecule attached with this R molecule, they will be broken down. So the salt bridges by which the quaternary structures of the hemoglobin is formed, that will be now broken down. So salt bridges on which this R is attached with T or this T will be now broken down. And this broken down, this phenomena, that is, once this one is broken down, then so this is the configuration which is known as the T4, and this is the configuration which is known as the RT3. So once the RT3 is formed, because of the breakdown of the salt bridges between the R and the T form of the hemoglobin molecule, the affinity of the oxygen towards the RT3 will be much more than the T4. That means affinity of the oxygen to bind with RT3 will be more than the T4. That means easily now second molecule of the oxygen will get bind with the another T molecule. So this is the first oxygen. Now the second oxygen will bind with the another T form of the globin molecule, and then this globin molecule, this T molecule will be converted to the R state or the relaxed state. So second 10 state of the hemoglobin molecule will be converted to the R state. So resultant effect will be the R2. Resultant effect will be the R2T2. And so this cycle will go on because of this cycle will go on as the R2 is getting formed. R2T2 has got more affinity. R2T2 has got more affinity of the hemoglobin than the RT3. That means third oxygen will easily get bind with the third molecule of the hemoglobin molecule, third unit of the hemoglobin molecule. So this will be now what's happened. This is T form. This will be O form. This will be O form. This is the R form. This is the R form. This is the R form. So first O2, second O2, and the third O2. So in this way, that means here R3 T will be formed. So from the R2T2, R3 T will be formed. And then again, this configuration has got more affinity of the oxygen to bind with than the T form. So then again, fourth molecule of the oxygen will get bind with this. So in this next step, what's happened? All T form of the hemoglobin will be now converted into R form, and thereby R4 will be formed. So in this way, as binding of the oxygen with one molecule of the hemoglobin unit. They initiate some configurational change because of the movement of the alpha 1 and the beta 1 dimer. 15-degree rotation from the main axis. And this configuration brings the ferrous molecule of the heme molecule towards the plane of the heme ring, and that pulls the proximal 8 of the globin chain towards the ferrous molecule, and this pulling action will cause the breakdown of the salt bridges by which other hemoglobins are attached or bound. And this breakdown of the salt bridges will make the second molecules of the hemoglobin to get bind with oxygen with more easily. Second molecule of the oxygen will bind with the second molecule, second subunit of the hemoglobin molecule. And this is how the T4 is switched over to RT3, RT3 is switched over to R2, RTT2, this will switch over to R3T, R3T is switched over to R4. So complete T form will be now converted to the relaxed form, and thereby oxygenation is completed. So this is how the during oxygenation the configurational change of the quaternary structure is taking place, and as in each step the binding of the oxygen is getting favored in each and every step. Binding of the oxygen towards hemoglobin molecule is getting facilitated, getting easier in each and every step, in step-wise fashion, step-wise manner. The entire phenomena is known as allostatic activation of hemoglobin molecule. So allostatic activation of the hemoglobin molecule is due to the change of the configuration quaternary structure of the hemoglobin molecule from T4 to the R4 state. And how this T4 is getting converted to R4, that mechanism I already mentioned. So if I sum up the entire this change of the quaternary structure in response to the oxygenation, then what's happened? So on deoxygenated state, hemoglobin molecule is very tightly packed, and this configuration is known as tense state, or T state. This configuration of the hemoglobin is known as tense state or the T state. Now, once the oxygen gets bind, on oxygenation, what's happened? As I told, the alpha 1, beta 1 dimer moves 15 degree from the axis in relation to alpha 2 beta 2 dimer, heterodimer. In relation to alpha 2 beta 2 dimer, 15 degree movement is taking place from the axis. That diagram I already mentioned. Now because of these things, this movement, what's happened? So this movement is, because of this movement, what's happened? This is known as the T2R switch. This one is known as T2R switch. Now, how this T2R switch is taking place? Because in this movement, results ferrous ion of heme molecule comes in the same plane of heme ring or hemoglobin ring. Ferrous ion of the heme comes in the same plane of the heme ring. This results pulling of proximal histidine residue of the alpha chain or the globin chain, alpha 1, beta 1 or alpha 2, beta 2. This will be pulled towards ferrous ion. And this movement results the breakdown of the salt bridges. By which other hemoglobin unit gets bind. So whatever salt bridges are there, by which all the hemoglobin alpha 1, beta 1, alpha 2, beta 2, they are bound, those salt bridges will be broken down. And as this salt bridges is broken down, what's happened? Now the affinity of oxygen to bind with next hemoglobin molecule or hemoglobin subunit is increased. This will be increased. So more easily oxygen bind to second unit more easily. And this cycle is going on. So repetition of this cycle continued. This cycle is continued. And ultimately what's happened? Because of this cycle, ultimately there is a conversion of T4 to R4 hemoglobin. This conversion is taking place once the 4 oxygen molecule binds with the 4 hemoglobin molecule of a hemoglobin molecule. That is, this T4 will be now converted to R4 because of the continuation of the cycle in stepwise manner. In each and every step, one oxygen easily gets bind with the next hemoglobin molecule, and thereby this process is known as the allosteric activation. This is the process, this is the things which is known as the allosteric activation or allosteric modulation. So by this allosteric modulation, stepwise manner, one hemoglobin binds with one oxygen more easily in respect to the binding of the oxygen with in the earlier step. So first step facilitates the second step facilitates the third step facilitates the fourth step. So this is how the allosteric modulation takes place, or oxygen binding to the 4 molecules of the hemoglobin becomes easier in each and every step. I hope the quaternary structure of the hemoglobin is clear, and as overall there is a structures of the globin is much more clearer to you. And if it is liked by you, please subscribe the channel, share it to your friends, and don't forget to press the like button. Thank you.